Mike, just for some background.
You are live.
Very well. Welcome, gentlemen. There being no ladies in presence. So ladies out there, hi. Last year, give or take a few days, I expressed some puzzlement at the obtuse code written by the feds and wondered why on earth would they write such monstrously long and convoluted. By happy coincidence, this week we discovered why the healthcare code was written thus. So much for old business. Three things. I read recently, relatively, that organic substrates for computing systems, neural networks, may have new life on actual neurons built by man. There's so much stuff out there that is offered apparently for free. And the price for acquiring this thing is a little bit of you, or yourselves. And most of us, exactly, you just give it up now and we'll find out, you have to give it up to find out what you've given up, paraphrasing Nancy Pelosi. So hurrah for the fourth interest group. There was a third thing. Alzheimer's, yes. Back in the 70s, we stopped using the aerosol deodorant, antiperspirants they were, because particulate aluminum in them. And they thought, well, you know, if you breathe it, it can cause dementia. So we're rid of that. And then I read about chemtrails and about how they're putting aluminum, micronized aluminum up in the air to reflect this, experimenting. Can we reduce the solar warming by making the Earth's atmosphere albedo a little higher? Well, it's a small price to pay, I guess. And then I read that Monsanto has a patent now on plants that are resistant to aluminum. But I read it on the internet, so I looked further and found out it's actually the USDA and the government of Brazil are joint part. So we concentrate here on clear code, on writing for good and not evil, and now I leave you to our presentations of the morning. Thank you again. Wait, there may be a comment. Is there a comment? Please, comment. Out really loud.
So the code is so clear that we won't have to run it to see what's in it?
That is our aim. This has been a standard, and so up the standard. I'm going off.
Switch. How's that? All right. Score. So today I have two things to present. The first is this talk, which I'll go into, and the second is a video, and we'll get to that in a moment. So I happen to not be keen on paying money for photo editing, and so there's this lovely program called GIMP, the GNU Image Manipulation Program. It's open source. It has a lot of Photoshop-like features, and the main and very cool thing about it is it's expandable with plugins. And of course, you know, being someone that wants to write software in Forth, I thought, hey, let's see what would be involved in writing a GIMP plugin in Forth. So the way plugins are done in GIMP is, at least I get the sense it was loosely inspired by the structure of Photoshop plugins. I don't know for certain the full history there, but they run as a standalone process, and this is presumably for robustness partially, possibly address space in the distant past. Basically what happens is that when GIMP starts up your plugin, it runs in a separate process. There's some communication using shared memory, little IPC, and you shuffle tiles back and forth. And the reason that tiles are used, tiles I'll talk about more in detail, but tiles are there for memory efficiency. And they have this user interface that's implemented with the GIMP toolkit, which has since gone on to be used in a range of other things. And the nice thing from the point of view of someone writing a plugin is that all the sort of hard stuff, or at least stateful stuff, is largely managed by GIMP. So, for instance, undo and all of the sort of layering and things of that nature. And you build. There's a library that's provided for you to link against to build a plugin. So the one big central idea with GIMP plugins, and this is similar to a lot of these kinds of image editing programs, is the notion of tiles, and it's a notion that actually bears a surprising resemblance to blocks in a weird sort of way, because it's basically it's a memory hierarchy thing, really. It's you've got these 64 by 64 times the number of bits per pixel, which is constrained for various reasons to 1 to 4 square tiles, and the idea is that if you're doing some operation on an image, you probably need information only local to that region, and if you do need something from neighboring areas, it's probably just neighboring tiles. So you want to make sure that you bring it into cache, sort of in a coherent way. And the key thing about this is that, unlike, say, imagine, storing each pixel row contiguously, you want to make sure that as you go through the image, you do it in tile order, and that you touch a limited set of tiles as you go through, or else you're going to wreak havoc with the various caching layers. And when I say caching layers, I mean not only in memory, but also people use GIMP to edit very large images. And so potentially you're even hitting disk and streaming through a large image, although less so today than in the past. And because you're also doing cross-process, you really want to make sure this works smoothly. So yeah, anyhow, that's that. So for this purpose, I decided to use Forth. The main reason is because it has relatively good ability to connect to C, and it does something kind of neat, particularly in terms of a GIMP plugin, because it does a sort of on-the-fly compile of the C code that you use. And one of the problems that you actually see with GIMP and Photoshop plugins is that you typically have to compile them, for each of the target architectures that you're on. And so if you're somebody who's distributing, one of these, you've got your usual cross-platform build problem. But with Forth, because you're compiling on the fly, you hand out source. It builds. It's not particularly slow to build, even though it's shelling out and running the C compiler, and then you get sort of everything initialized at the point that the plugin loads. So the good thing about Forth's ability to talk to C is that you can bridge from Forth to C, but although there are some deprecated libraries to go back the other direction that are more low level, the recommended bridge to C is really in one direction. So you have a little bit of an issue around callbacks, and I'll talk about that in a second. And I have no idea what that bullet point was supposed to mean. Focus on filters. So the main thing is that you're... What in the heck was that supposed to mean? Anyways, so the main idea is that what you have to provide in your plugin is some information about the layout of the preview panel for your plugin. So if you're doing a filter, you may have various options that you want to specify, and then you have to actually describe whatever filter that you're going to implement. What did I end up having to do? To deal with libgimp, which is assumed to be something you're going to be dealing with mainly from C, I needed to Forth lets you declare a bunch of C interfaces, and so I had to declare all of the various libgimp and GTK functions that I wanted to use, and you have to kind of regurgitate a little bit of what's in the header files for each of these to bridge the mismatch. But the big thing is handling callbacks, which unfortunately the sort of out-of-the-box support in Forth is a little dubious on. And in particular, this is where you're handing a function pointer to something in C, and then you want it to jump back into your Forth code later. And it turns out that there's only really two places that you actually have to do this when you're dealing with a GIMP plugin. You need to do this when you're in the sort of main loop of the plugin. You need to register a bunch of handlers for, here's what you do when you want to query me about what kind of plugin I am, and then here's what you do when you want to actually run the filter on whatever region. And then the other place is that when you actually get asked to do a preview of your filter, you're then asked to potentially, as a part of that, do another operation, sort of a second layer in. So you're first asked, give me the dialog for the preview, and then after that, give me do some previews. So what I ended up doing as a sort of roundabout workaround was moving all of the calls into C code off into other threads, and this way I could sort of keep the Forth code blocked in one place, defer off and say, okay, I'm going to call this handler on another thread, have it block. When it's ready, it signals back to the Forth code, which can then move along on its stack, and then when it goes and needs to block this for the second layer, I can have it block. And so you're sort of keeping the Forth stack segregated from the C stack, which ends up sort of sidestepping this, although you have to do a bunch of shuffling around. That was actually the biggest piece of hassle with it. So it ended up being about 400 lines just to sort of go and declare all of the huge orifice of the C interface to these libraries. And they're kind of, they're fairly Baroque libraries where you're sort of, you can set up different kinds of widgets, and it's a whole widget, library is actually where a lot of that comes from. And you're sort of, there's a surprising amount of, functions where you're passing in, 10 different things and whatnot. Preview UI was a big chunk of it as well. It's actually very Baroque to just, I want a preview panel where I show the preview image and a checkbox for the button and this sort of thing. And then about 100 lines to manage the actual traversal of the tiles. And what I decided to do with the tiles, so in general, when you're writing a plugin using this API, you can sort of do whatever you want in terms of how you traverse the image data, but if you choose badly, then you'll get terrible performance. And so rather than support all of the different possibilities, I focused on saying, well, I know that going in tile order is the preferred form. So I assume that for any reasonable filter, what you're going to want to do is traverse the output area tile by tile, and then during that process, you may need to access for input some region of tiles around you, but that you're really only going to traverse the output area once. And this actually, from what I can see of the built-in plugins, actually matches reality. In the vast majority of cases, if they do something more elaborate where you need to do some further processing, they create their own off-memory buffer, and usually those plugins don't actually scale to something that won't, fit into memory or will be slow with the amount of memory you've got. And then there's some 50 lines of random stuff. So it wasn't, too bad, about 800 lines something of code. So here's, with all that GARP under the covers, here's a sort of a boilerplate, half of a boilerplate plugin. So the first thing is just there's a ton of things you have to declare about what your plugin looks like. So you have to tell it the name of your plugin to display, and then the other key thing is that there's a big menu hierarchy of where your plugin shows up under filters, and then there's different buckets. And so this one, for instance, I'm sticking under artistic, and then there's a bunch of other you need to say, well, here's the text for when you're showing a preview, and there's a few different fields, a description, a copyright, that kind of thing. And then here's a very simple plugin. And so down at the bottom, this is the sort of main entry point, and then you declare a kernel for the plugin. And all it really does is, so this get chunk operation is basically saying, well, here's the input region that I want. And the interface I've picked is just, you assume by default that you're at least going to want the tile, the input, the same tile that you're considering currently, and then you may want some region around it. And so the 0 there is just, I don't want any additional region around it. So if you want a larger region of some number of pixels, then you specify that. And then so this is called once per tile. And for each case, what happens is that and actually I have some, so declaring that here's the kernel of your filter, and then you read in the chunk, and then for each you can loop through each row of the tile, right? So this H is in this vocabulary is just down in the one tile, and then here I'm pulling out is just a memory pointer to the memory region that contains the tile data, and then you have a stride, which is the width of one row. There's a possibility because of the way they lay out in memory that you may go through one row and then the next row is not immediately on the following line, but potentially further along. In practice, that stride is probably equivalent to the width, except in extraordinary cases. And then the same thing with the input region, except that in the input region, you're assumed to know how much padding around it you requested. And so for the input, a copy is actually made out of whatever tiles, because you may be asking for a region larger than one tile. And so you iterate around the rows, and then W the width, and you're going across each region. And so for this particular one, I'm doing an operation per bit plane, BPP bits per pixel, and then I'm simply doing an operation where I'm reading. So for the duration of the loop, I've got 2 pointers into the input and output region, and I'm just doing a little fiddling around in this particular filter, and then stepping the 1 plus swap is just stepping through that region. That worked poorly. Okay. So that was sort of to get the basic plumbing, and I'll show you what that particular filter looks like in a moment. The thing I then wanted to do with this is to take the haikus and represent them in this form so I could use them in GIMP. And the key thing here is that the haikus think of the world in terms of you're doing a computation per pixel, and so they don't worry about tile regions or whatnot. You're not using information from your neighbors, and there's not in the original paradigm of it. There's no notion of using the input image at all. And there's some weird non-standard words that I use in the haiku vocabulary. And then the other big thing is that the haiku vocabulary assumes a float stack rather than an integer stack. So I had to sort of compensate for all of that. So I came up with a sort of a bridging layer that lets you take one of my haikus and you still have to rewrite it, but it's fairly minimal. So you end up with something like this if you had a haiku that was your XY gradient, it looks something like this. And then you can transcribe one of the other ones, and there's sort of a per word you're breaking from the front of practically everything to move over to the floating point stack. And then let's go and actually look at the thing. So oops, there we go. And so when we fire up GIMP, so at startup, GIMP goes through and it actually goes out and checks to see if there are any new plugins. It didn't do that that time because there's nothing new, but the first time that it notices your plugin, you place them in a certain dot directory. It's a little platform specific. It goes and interrogates the plugin and asks it all those questions about what's your name and this sort of thing. And then the result is that under filters, and I put them both under artistic here, you'll notice that now there's actually two of them. I named my sort of basic test one distortional, and then there's a fourth haiku one here. Before you can actually select them, you need to, let's not look up there, you need to actually have an image. So I'll just create an image here. And let's put some data in here. You can sort of draw around in there. And then so this is that first one I showed you, the little direct one. And so there's this preview region, and it's here because I did an operation that was using the value of your position in the tile. You can kind of see where the tile boundaries are, at least horizontally. And this preview pane is sort of it's only asking the plugin to render that region as you move. So if I hit OK, it goes and does the filter, and so you transform your image appropriately. Now, for the haiku filter, I had originally intended to explore, adding to the haiku vocabulary access of the region around you. I haven't gotten that far, so what I've got here is basically just a version of the haiku that can run in this context. So, for example, so you notice there's this little text region here, and that's where you place your code. And it's so if we take like this this gradient, for example, oopsie, that's not the right. That's my mouse is acting funny. So I've done a bad thing here. Let's see. Demo fail. So the one unfortunate property of these plugins is that even though they're supposed to insulate the application from crashing, I have discovered that this does not work consistently. And one area where it doesn't work consistently is there are a couple of places where if you don't respond to the host at the right moment, it does not bring down GIMP itself, but it brings down your plugin. So let me not tickle that. And one way to avoid that is to turn off the preview, because then it's not sort of live. All right, so, oops. So you paste your haiku there, and what happens is that if I now turn on the preview and hit OK, you can run the haiku. And what's happening there is that text is being handed off to GForth, executed in a kernel, and then handed over to GIMP. I can do a more elaborate one here. Let's see. Now this is one that materialized recently. I'm going to turn off the preview because I'm having bad luck with that today. And turn back on the preview. And this one's cute. It's it's a very small, minimal one. It's an actual haiku that someone added. It's somewhat lost in the in the recent plumbing. And then let me just. Well, anyways, that's how are we doing for time?
Yeah, about 5 minutes.
Okay, then I'm going to move on to the video. So I will likely experiment with this more. One of the things that I hope to do is make it more robust. So it's a fairly straightforward interface to add something now. But as you notice, like when I'm pasting things in there, what's happening is it's trying to execute it. There's a bunch of things that can fail when you paste in Forth code that doesn't run or doesn't compile. And in those cases, it can throw the plugin into an angry and confused state. The nice thing about having it in the context of GIMP is that it solves a problem that I've had for a long time with the haikus, which is I would like to potentially think about like what happens when you have an input image and you're doing a filter expressed in the haikus. But on the website, it's unclear where I would get the images from. I don't necessarily want people uploading random images. So doing it in the context of a plugin may provide me a solution to that. Now I would like to present a video that is a compendium of the rather impressive range of things that folks have put up on the haiku site. And I apologize in advance. The sound is not all I'd hoped for. What I did for the sound is maybe a year or more back, I'd done an experiment with having the haikus also generate audio. And after some fiddling, I sort of settled on a pentatonic scale. So I took some of the ones that use audio and I put a few together, and it's not the greatest audio, but it's at least all sort of Forth. So what you're seeing, with the exception of the titles, is all sort of 100% Forth. And the other thing that I did for this video is that while the haikus are normally a square region, and there's a sort of a fixed image space from 0 to 1 in both dimensions. Because I wanted to do widescreen, I've extended the haikus out, so you're sort of seeing the region to the sides of either haiku in order to get sort of fill up the screen. So without further ado, I present. No, fiddle. It's not that.
There should be some kind of.
Any questions on either two?
How did you capture the image?
So I added there's been a number of slideshow options. I'm going to turn that go off. There we go. There's a number of slideshow options that I've added, and I added a third one for this one that fetches a batch of about 40 of them, and then lets me sort of step through them, and then I used a capture board, Hoffenpog, I think is the company name, to capture the video, and then the audio I then mixed in later with After Effects. And unfortunately, one of the drawbacks of this is that because I was just sort of grabbing a batch of 40, this is sort of each one you saw is a separate submission, but many of them are sort of somewhat duplicated because people can say, let me create a derived work, and very often people will do very little or it will change relatively little. And so there's a certain amount of repetition, and I had only I was sort of doing editing only in blocks of 40, if that makes any sense, which seemed, yeah. And then the later ones I zipped through because it was just too much. And believe it or not, I didn't get even halfway through the database of stuff.
Some of the more complex abstract ones, how long is the code
So what's it? Oh, sorry. Let me repeat the question. The comment was that some of the more abstract ones are very neat. How long was the code for them? In general, there's a cap on how many cycles you're allowed to spend in the haiku. I did this mainly because I didn't want folks, particularly when there was a JavaScript implementation, I didn't want folks to go to the site and have it just halt because somebody had hit it. So they're constrained by that. However, there's no actual constraint on the size of the haiku. So I don't know offhand, although my general sense is the vast majority of them are no more than maybe, well, most of them are no more than maybe 20 lines, and the biggest ones are probably in the realm of 60 or 70.
How much time did you invest in each image?
So the thing is, most of these images were submitted by other folks actually online, and so my investment was, some of them are actually my creations. There's a sort of a smattering of them that are ones that I had done sort of the early days. Some of them are derived works from the ones that I put in initially, but the bulk of them actually are. There's a number of folks, particularly in this last year or so, that have shown up, many of them in Russia, some of them are demo sceners that are interested in producing code that's very small, and they actually kind of compete. Some of them, they compete as to how many characters long the haiku is. And so some of those are the neatest, like the Pac-Man is just astounding. It's a tiny little, 10-line thing that you look at it and you have, no idea how it's, how it works.
I look like a goof, but I'm doing a sound check on myself. Excellent. Huh? I am getting sound, yes. And I have video. Yeah. See it? Perfect. Okay. My name is Sam Falvo.
Listen up, Sam.
And I'm here to talk about a topic which will undoubtedly get me cast as a heretic amongst the community. I'm going to talk about compiling stack architecture code, obviously using Forth as an example, but it doesn't have to be Forth. Any kind of stack architecture code qualifies to an architecture that is register dependent. So why would we want to do this? Well, just by looking at that list alone, we see that registers are pretty much everywhere. Intel architecture, obviously, we have a ton of registers in those. ARM cores, Coldfire, Parallax, most of your deep embedded processors nowadays have lots of registers, courtesy of small transistor sizes. MIPS, PowerPC, and SPARC architectures, believe it or not, those are actually still relevant. Ironically, not in the embedded space, but in the supercomputing space. I list PowerPC because it's a foundational instruction set, but if you look at most of IBM's modern architectures, the Power 8, for example, instead of deriving from Power 1, they actually derive from PowerPC. And of course, Oracle with its SPARC architecture, 64-bit, 20-plus cores on a die, you know, that sort of thing. Lots of interesting stuff. And of course, the RISC-V architecture, which is going to be the foundation for the new Kestrel. And the reason I went with that is because it offers, for my needs at least, a good blend of code density and implementation simplicity. Only has about 45 instructions or so that I need to implement, but everything else is fairly traditional RISC. FPGAs are very well adapted for RISC architecture, so it seems like a good fit for that. Had I gone with MISC, I would have just a naive implementation of MISC. It would have consumed a gratuitous amount of memory resources, which I wasn't prepared to invest, particularly since fetching 64-bit quantities from SDRAM on that board is deeply expensive. And then if I wanted to compact that code down, I would have ended up implementing a very complicated instruction decoder comparable to a CISC. So yeah, that was my rationale for that, which in turn got me interested as to how to compile Forth for it in a reasonably effective way. And it is much, I won't say much, yeah, it is much harder to compile for registers than it is for a stack architecture, obviously. But I won't say it's impossible. With the good selection of algorithms, you can actually get very near to optimal code. In fact, this is the origin of the myth that says that compilers are oftentimes better than human people at writing assembly code nowadays. I would say that that's true if you're a naive coder, but if you're actually deeply involved with the microarchitecture of your target CPU, then it's an obvious lie. But when you have this kind of automation, you actually get to a point where you're good enough. And by good enough, I mean within a few percentage points of optimal. Actually, before jumping on that, I was up till 1 o'clock in the morning working on this. So there's 4 major components to being able to do stack compilation to registers efficiently. The first is you want to reconstruct your abstract syntax tree from a theoretical, perhaps non-existent infix language. The reason you want to do this is because it reestablishes context, which is something that is important, especially when dealing with Booleans, as I'll show you a little bit later. Your internal representation, strongly recommended. Take a look at static single assignment. Register allocation. A lot of people like to use graph coloring allocator. I don't understand why. It's very complicated and it doesn't produce optimal results. when you have your internal representation in SSA form, you actually have all the information you need to implement the clairvoyant algorithm, which is the optimal register allocation system. And then if all of that is more complicated than you would like, then you can alternately use something called a destination-directed code generator. I'll only touch upon that briefly here because that's of marginal interest, primarily because it's described by one academic paper that is so clear that you basically understand it after reading that one paper. But the top three are what I'm going to be focusing on in this talk. So why do you want to reconstruct the abstract syntax tree? And it basically boils down to how do you efficiently handle Booleans. And the reason you'd want to efficiently handle Booleans is because ultimately you're going to make a decision based on them. Now there's several ways you can do that. One is you can treat Booleans as bit masks. This is the approach that traditional Forth has preferred over the years. The reason it's very efficient is because you set all bits as 1 or all bits as 0, which allows you to use ands and ors to select one or amongst several different alternate values in a computation. And as you can see here, three instructions is pretty efficient no matter what your architecture is. But sometimes when you're going to use a Boolean to make a decision, you can actually, assuming you're representing them as bit masks, you can lead to inefficiencies, which in turn leads you to a policy of avoiding if statements and avoiding loops and things like that at all possible times. Because as you can see here, there's a lot of operational overhead trying to reconstruct a decision tree based on a bit mask. So you can go with a kind of a hybrid approach, which is what most of your 8-bit and 16-bit and even some 32-bit architectures do, which is they use flag bits. And you have dedicated compare instructions for these to set these flag bits, and then you have a selection of jump instructions that operate on these flag bits. These are kind of in the middle of the road because you can either go, because you get reasonable efficiency for making decisions, but if you want to reconstruct your bit mask from that, it's only a handful of instructions as well. So this is kind of middle of the road performance-wise. But then on some architectures, especially on a lot of risks, your Booleans don't actually physically exist. You actually encode the decision that you want to make based on that Boolean directly in the instruction. So here, for example, on this top instruction here, this BLT x1, x2, L1, what I'm doing there is I'm comparing register x1 and x2, which in this case happens to be 65, and if less than, jump to label L1. So all of that happens inside a single clock cycle. All of that happens inside a single instruction. There's no flag bits, there's no pipeline stalls because of that, and so forth. So when you're dealing with pipelined architecture, which I will be, this is actually the optimal approach. When you have that kind of performance, avoiding loops is no longer a consideration. So the way we do this is the compiler maintains an understanding of what the code has seen so far, if that makes sense. So in this case, I'm pushing the literal constant A, which is ASCII code 65. And then I do the same thing with character Z. Next, we see a 1 plus, which increments that. So since the compiler would know what 1 plus means, there's two approaches to this. Either we can reify this code into actual machine instructions and then compile an increment. But since we already know what the values are on the stack, we may as well just do it at compile time. And then something like within could be an immediate word, which in turn compiles a complex decision tree. And so in this particular case, I'm representing that decision tree using abstract nodes. Now, I could have just as easily done this with more traditional, to-dupe and blah, 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 and actually reconstruct it manually. But the end result is this. This is what you would normally get. Like if you were to write this in C, it would be something like if x greater than or equal to 65 and if x less than 92, then blah, blah, blah. And you would have this abstract syntax tree node representing the conditional of that if statement. Hello. So once you have that node available to you, because it's semantic and not what am I trying to say? I'm sorry, I didn't get much sleep last night. Because we have this context available, we can actually peek down into the abstract syntax tree and be able to say, okay, you know, we're using this X value here twice, so we may as well just stuff that into a single register or something like that. But we'll get to register allocation in a little bit. We'll do it a little bit differently using SSA representation, but that's the kind of thing that you can do. So if you're doing it inside an if, as we are here, then we know that this and maybe these operators don't necessarily have to compute bit masks. You can actually, you know how to encode them into compare statements and jump statements if you need to. Now, if instead I didn't have an if statement, I had something like hex code 20 XOR, then I would know, okay, this and statement is a bit mask, is a bitwise and we can compile the code appropriately that way. I'm sorry? I thought I had 20 minutes.
How much more do you have?
A lot. I thought, okay, well, anyway.
How about you take 5 more minutes?
Sure. So this is what's called single static assignment. Basically, you assign stack cells, in this particular case, to unique variables. You assign them once and only once, and they last forever, at least until the end of the function. So here you can see, for example, I reuse codes appropriately. Typically, they're written out that way, from top down. They have various attributes. I'll go ahead and, since my time is significantly limited, I'll do a separate presentation on this. Getting into clairvoyant register allocation, which I'll demonstrate shortly. Regardless of register allocation, though, realistically speaking, we have so many registers, and since we're emulating a stack machine inside, you almost never spill. So you can actually get by with a suboptimal register allocator and actually do pretty well. Why you would want to compile code like this? Well, my interest is in graphics as well as system software. Applications, of course, you want real-time user interface. Not that Forth is a significant impediment to real-time UI. I mean, obviously, we've seen plenty of examples where the contrary is true. But when you're running a lot of things, it all adds up. So I want to be able to streamline all that. Also, fuzzy logic and calculus calculations involve a lot of stack permutations, I find, as my attempt at writing a video game has taught me. So I'm looking to optimize that as well. There are certain trade-offs, looping tricks, such as begin, while, repeat, then until constructs. Those are strongly discouraged because that will interfere with the code generation. It is, of course, very complex for the environment to be able to do. But here's an example, converting a degree Fahrenheit into both Celsius and degrees Kelvin. Here's the single static assignment representation of that code. This is a register allocation map. Basically, the vertical axis represents when a term is introduced, and the horizontal axis measures how long that term is used. And this is all statically deducible from the SSA form. Based on that, we can assign registers, and there's the resulting assembly code. Now, assuming that loads and stores are single cycle, this actually takes about 13 clock cycles to complete, which is actually not too shabby. It's only 3 cycles more than the individual operations in the Forth code itself. You'll notice that the dupe instruction, there's no machine code corresponding to that because all stack permutations happen at compile time, not at runtime. Did I meet my deadline? Okay. Any questions while I still have the floor? Yes. How do I expect performance to vary compared to a stack implementation? Considering contemporary bus architectures, I would expect it to actually run a little bit faster, primarily because everything is optimized for pipeline operation. SD-RAMs, for example, you give it one address and it bursts a bunch of data to you. And a lot of SD-RAMs actually have 2 or 3 banks. So what you can do is you can give it 2 or 3 addresses, and then it will sit there and it will burst them in the order that you give them. So for register applications, everything's all optimized around registers these days. Also, again, stack permutations are optimized out. Now, the degree to which it runs faster, I would say maybe a handful of percentage points, 5% at most. And the reason for that is when you get a really optimized stack architecture where you have a correspondingly compatible memory subsystem for it, your stack permutations only take 1 cycle, right? But you look at this previous code, I've got loads and stores, right? So you can't win for losing.
Okay, and the list, Dave, the lunch list going around now? All right, if anybody has not signed up for pizza or whatever they're having for lunch, they will be in the back. Go now. Sandy gets the mic.
Yes.
I'll let you go.
Thank you.
I trust you, Dennis. Yeah. Oh, yes. Right.
Shouldn't do that.
Shut up. Okay, can I just stuff it in here?
Just shove it wherever it goes.
Don't say that. Okay, I'm not going to...
Everybody else, please, quiet.
Okay, guys, my name is legally John... John Bumgarner, but I have a nickname which everybody uses these days. It's Sandy. My students and everything else, so you can use whatever you feel like. I've been in the fourth world for a long time. Right, Chuck? It is practically the only language I ever care to use. Now, I've been doing some work recently with a particular processor which I enjoy reading about, and I've now designed a system for. It does have several Forths available for it, and it is the Parallax propeller chip. I don't know if you've ever heard of that one. Who in here is at all familiar with the propeller chip? Okay, good. It is basically a multiprocessor, but in a totally different way than we are familiar with from especially Chuck, because each one of the 8 processors inside is completely independent, small processor itself. They're all identical. They all have the same resources, and they are engaged by a round-robin hub that powers each one, but they all run independently as well. Like many multiprocessing systems, the prop can have peripherals built into each one, so you could have 8 serial channels if you so chose. And one of the designs that I am going to talk for a few minutes about does have, in fact, 8 serial channels. I have worked now for some time on doing test designs. Most people here probably have heard of Express PCB, which is a free software system that is terminally stupid, but very nice because you can do anything you want to build your printed circuit board, and the people that run the thing have reasonable prices and reasonable turnaround rates. So you can build anything you want. It is one of the easiest systems I've ever used. I've used some very high-end printed circuit boards with auto routers and all that stuff. So I prefer to do it myself. So I built a couple of test designs. One of them is a printed circuit board that fits in a nice enclosure. Oh, by the way, we have my partner and I have a small company called Video Timers, and we make a video timing gadget, and it goes in a nice enclosure and so on. So I made these boards to fit the enclosure. So you could buy an off-the-shelf nice enclosure, and for a couple of bucks, we'll even send you a front and rear panel that fits the switches and lights that happen to be on this thing. So you could have a totally blank circuit board with switches and lights and a dip switch, a couple of RCA connectors for video. And you could build yourself something in a nice looking box. Anyway, the first design that I want to speak a few minutes about is a totally breakout board one. From Parallax, the Propeller Mini board, from Adafruit, the GPS module that they have, and from SparkFun, a graphics output chip using the Max 7456. So these breakout boards all fit nicely on the board, along with some pretty indestructible power supplies. These power supplies have been checked out for up to 40 volts. So if you wanted to build a portable unit, which what Video Timers does, you can build a fairly robust portable system with it. You can plug it into, for instance, a 24-volt car system and not worry about things. So the first design has these breakout boards, and they are connected to the switches and lights. That's one of the unique features about the Propeller, is it's so easy to connect it to various things. You just wire up the most convenient pin geometrically to whatever LED switch or whatever you want. And then internally you connect it to one of the cogs. And then each one of the cogs has its own I/O structure. So it's very simple to build, rather than taking port A, line 3, which is over here, that wants to be connected over here, so you've got to run things, you know how it goes. So this one design, with the breakout board one, is freely available to anybody. Just send me an email, and I will be happy to send you the entire setup on the Express PCB. And that way you can, if you like, take a look at it, or even have a board manufactured, or perhaps have talk to me about, we'll go, and do manufacturing together or whatever. The second design is, again, using a propeller chip, but because of the fact that in our business of video timers, we are pretty heavily into GPS timing with pulse per second accuracy, we found that here's the history. The company called Global Top, excuse me, I have a little memory problems, and these red patches aren't makeup. They're results of my fairly heavy-duty chemotherapy that I'm doing right now. And that's one of the reasons I'm less prepared than I wanted to be today. Yeah, like can't remember stuff, syndrome. The original manufacturer of the GPS, the 406A, stopped making it and introduced a 506A, but they changed the internal code in the thing and lost all fiduciary alignment with the GPS, the universal UT second. So now it issues a 1 pulse per second, but it's at any phase angle you want with a real second. And so we could obviously not use that in our timing product. So it's kind of bad when all of a sudden they cut you off at the knees on a part. They say, well, here it is, and it works just like it, and it's more sensitive, and everything's better. And we say, everything is totally useless. So we had to go looking for another one, and I can recommend highly the GlobalTop PA6H, which is on the Adafruit board. It's an amazing little chip. It is very sensitive, and it's very accurate. But in finding that one chip, we had to go through a lot of comparisons. Like, for instance, how in the heck do you find an accurate GPS, PPS signal? What do you compare it to? Well, you intercompare among processors, which gave me the idea for the second one, the propeller chip. It has 8 serial channels, and it will accept 8 external inputs, serial channels, but with a capsular register for the PPS signal. So it is possible to build with this one, and the design's freely available, like I said, to build so you can do a statistical comparison of many things. And so that's a board I'm going to make a couple of, so that in the future, anytime you want to go and find out what is a good timing chip, you can try it against several other ones and do a nice comparison, a statistical comparison of it. So I don't know if anybody's been faced with that problem, but it's a really kind of a daunting thing. What is the universal time? When is it the second go? Exactly. Everybody's used to GPS, but because of the fact that this one company switched and then the code inside it now is totally unreferenced to it, even though they claim it's PPS. So if you went and bought that chip thinking you were getting one, you'll get something that goes once every second, but its relationship to the true UTC second is anybody's guess. Okay, so there's 2 designs available. I'd be happy to supply people with support and or the designs. Just contact me and I'll send them out to you. I was going to try and bring here an actual board, but I ran out of time and I had to push off a chemotherapy thing until Monday, and that was bad enough. So I just didn't have time to finish it, guys. I apologize. I apologize to Mr. Jaffe for not getting back to you in a prompt manner, but hopefully you'll understand. So that's it for me. Any questions? Yes, sir.
How accurately do you get the second tick?
It depends a little bit on the particular one, but typically they're well within a microsecond. The higher end ones, for instance, available from Trimble and so on, are within a few nanoseconds. For instance, 20 to 50 nanoseconds is probably a reasonable number. So it's pretty darn accurate. Yes, sir.
On the early receiving L1 channel,
The which?
the ionospheric disturbance, you typically get no better than 100 nanoseconds.
Right. That would be due to the fact that you don't have any WASP and stuff like that available to you. But sub-microsecond accuracy is pretty darn good these days. You know, here we are worrying about 100 nanoseconds. Yeah, right. Yeah. Do you have a question? No, sorry. Yes, sorry. Yes. The Forth that I'm using is the propeller Forth, available from Parallax and fairly well supported. There are several different Forths available. The propeller Forth is probably the most useful in the sense that it's supported and so on. But the most interesting one is called Tachyon Forth. It is lean, mean, and very quick, but I just don't have the time to play with something that isn't, well supported. I don't want to do a Forth development. I want to build something with Forth. They do. There's a very active group and so on with it, and it's easy to download the thing. The easiest way to get up and running would be to buy a $25, I think it's about, getting started board with a propeller chip on it and a bunch of resources. And so that thing plus a download clip that goes onto it, and you're home free. Which one? The smart boards, yeah, right. Smart boards builds, I think, one that's for that as well. And they're nice because, if you're not I've got a microscope and fairly steady hands and everything, so I usually go ahead. I can work with anything practically down to 0.5 millimeter myself, but smartboards are nice because all you have to do is just solder and push it in and make your connections to the chips. It's great stuff. Okay, does anybody not know about smartboards? It's the German smartboard, yeah. It's great stuff. Those guys have done a real service for those of us that, or those of you guys that really have a difficulty. Like, the nice thing about the propeller chip, though, is it comes in a 40-pin dip. So anybody can do it. You can plug it into a socket. But I use the QFN1 version of it. So there you go. Thank you for your time.
Give Harold the microphone.
Oh, yes, I will.
Thank you.
How do I do this? Thank you very much.
No.
There you go.
Is this working? Okay. Is this supposed to work? Okay. All right. Cool. So my name's Harold. I'm going to talk about the RCA 1802, which is the era of the original Forth implementations. It came out. 1802 came out in 1976. I think the original Forth was 1969. So this was an interesting era. Forth was designed around resource-limited architectures. This is probably the worst of the architectures that were ever designed in terms of resources. And so the challenges involved in getting it to work. So I said it's manufactured in 1976, and the one in the picture I found on the web has got a date code of 7653, the last week of 1976. And I have one of the same vintage chips on this board here. This is an RCA evaluation board. And the date code is the same, 7653. It must have been a busy week at the RCA factory someplace building these chips. It's based on static CMOS. At that time, the microprocessors were NMOS, fairly high powered. Today, everything is CMOS, but that was one of the first CMOS processors. It's totally static, which means that you can clock it down to 0. And in fact, one of the techniques to use for debugging this thing is to clock it at 0 hertz and single step it with a push button and watch what's happening on the bus. And you debug literally your code, single stepping in hardware. It's very, very low power. CMOS, one of the advantages of NMOS is its power. There's obviously no heat sink on this thing. You look at any modern processor, most of the weight of the thing is the heat sink. This doesn't need one. And it's so it can be battery powered, and it was used in several space programs, both because it's low power and also because it's radiation hard. If you take any modern microprocessor into space, it will die in cosmic rays. This technology is able to operate in high radiation environments like outer space, and it was used on the Galileo spacecraft that was launched in the late 80s, and I believe a couple of years ago we crashed it into the surface of Jupiter just for fun, and there were some 1802s on that spacecraft, several of them. And you can still get it. Intel still makes it. There's probably some military program someplace that still has that thing designed in, and you still need to be able to manufacture it, and so you can buy them from still. There's even an updated data sheet and everything. There's also some computing activity around the 1802. In the 70s, there was a hobbyist computer called the ELF2, based on the 1802. Somebody's resurrected that, and they're selling an ELF work-alike. Actually, it fits in a can of mints, you know, the Altoid cans. You can buy an ELF that fits in a can that size and still lives in real hardware.
It's called the membership card.
Correct. It's a guy called Lee Hart does. So what are the resources available in this processor? Just, you know, to step back a bit, everybody thought on computers. This is not a computer. There's no OS. It's bare metal, literally bare metal. It's the equivalent of when you boot up your computer and the BIOS runs, you know, it starts from nothing. This thing has absolutely nothing. There's no keyboard. There's obviously no disk. There's no file system. There's no operating system. There's no mouse. There's no Ethernet. There's no Wi-Fi. There's, you name it. Any of the modern interfaces do not exist. There's not even any serial I/O on this chip. In terms of I/O, you get, count them, you get 4 input bits, 4 1-bit ports, and you get 1 output bit, the Q bit up there, and everything else you build yourself. So the kind of the hello world of bringing up an 1802, if you can get that output bit to toggle, then you've got something running. That's your, you know, your initial boot up program, and there's actually one of the instructions is set the Q bit, clear the Q bit, and we'll see. We'll use that later on actually to create serial I/O. There's a 8-bit data bus. It's an 8-bit processor. There's a 16-bit address bus, so it can address up to 64K of memory, or a flat memory space. And it's actually multiplex, so you have to latch the high order part of the address and then the low order part of the address. So you can do memory mapped I/O. There's a little I/O bus. For some reason, it was traditional to have separate I/O buses. And so there's a 3-bit I/O bus as well, which I don't use, but it's available. And that's the whole processor. So when you look at this board here, this is an evaluation board that RCA put out. It came with an 1802. It came with 2 RAM chips. These are 256 by 4 CMOS RAM chips. That's 1K bits each. So that's 256 bytes. I've expanded it. I've got a K and a quarter of RAM on this thing now. It's really, you know, it maxes out at 4K of RAM if I filled all these sockets. But it has a ROM as well. So this thing can boot from ROM. This is what this board does. This has actually a 2K UV erasable ROM. The label on this, which is peeling and yellowing, says it was last programmed in October of 1980. So its ROM last came up 34 years ago. Actually, it doesn't work today. I have to fix it. So booting it, there's a couple of ways of booting it. Either you put a ROM in at location 0 so it starts executing. There's actually a way to load RAM by pressing some push buttons. And, you know, and doing a DMA directly into RAM, you can in fact boot it without a ROM, but that's very painful. Obviously, trying to program in binary, you know, one bug, you have to start over. It's not simple. So this will be based on a ROM. What are the processor resources? In some ways, it has some echoes of what today would be called RISC. It has a register file of 16 registers. These are 16-bit registers. Somebody's connected me to an internet. But these are not really general-purpose registers because you can't do arithmetic in them. All you can do is point to things. So you have 16 registers. They're all the same. They can be used to point to things. One of them is used as a program counter. This is really what makes this thing unique, is there is a program counter selector. So most processors, all processors, as far as I know, have a single program counter register. This has a possibility of 16 different program counter registers, and you pick which one you want with a P register. So there's a 4-bit P register that selects a program counter. There is another register, a 4-bit X selector, which selects one of these things to be the index register, and all arithmetic operates between the memory location pointed to by the X register. So you can't point to, you know, can't do arithmetic on 2 different locations in memory in one instruction. You have to move the X register to point to different places. There is a single 8-bit accumulator, the D register, and there's a 1-bit. There's a 1 carry bit. So that's the whole thing. So the interesting thing is the ability to select the program counter, and that's what I use to create the Forth inner interpreter and some of the low-level words. So what are the instruction set? The instructions are all 1 byte long, so there's 256 different instructions. Most instructions take 16 clocks. As compared to today's processors, which do like 5 or 10 instructions in 1 clock, this does 16 clocks to do 1 instruction, so it's a couple of orders of magnitude slower in terms of microarchitectural efficiency. The clock, max clock rate is 3.2 megahertz, which means you get 200 kilo instructions per second. And these are, of course, 8-bit instructions. So all the arithmetic is 8 bits. One of the operands in the arithmetic instruction is always the D register. That's the source and the destination. And the other operand in the arithmetic, the memory location pointed to by the current index register or an immediate. Immediate is essentially the value in memory pointed to by the program counter. It's the byte after the instruction itself is the immediate operand. So you can have either an 8-bit immediate or an 8-bit memory reference operation. You've got 256 instructions. You've wasted 11 instructions just to address the different registers. So 11 of the opcodes out of the 16 high nibbles address the different opcodes, basically shuffling data in and out of the D register. Since you can't do any arithmetic in the general purpose, the index registers themselves, you have to shuffle everything in and out. And so you've wasted a lot of instructions just doing that. There's a branch instruction, a short branch, 256-bit offset, but it's not a relative offset, which is traditional nowadays. It was even simpler just to replace the lower byte of the destination of the PC. So you find yourself, you can jump within the current 256-byte page, and it's very annoying. You add a couple of lines of code, suddenly one of your branches goes to another page, and your assembler fails because your branch is out of range. So there are long branch instructions which you can address anywhere in memory, but they take 3 cycles instead of, they take 24 cycles instead of 32 cycles. Sorry, 24 cycles instead of 16. So that's the instruction set. That's what you got to work with. So what you don't have is a call or a return instruction. A call instruction in a modern architecture means I go someplace in memory, I move my program counter to some other, but I remember where I came from. So there is no call. There is no stack, which is like, by the way, it's like a RISC processor. RISC processors don't have hardware stacks either, but they have a thing called a link register, which remembers where you came from. So what we're going to do instead of the call is to use the set program counter instruction, which does have the property of remembering where you came from. When you set the program counter to another register, the old contents of the previous program counters are retained, and you use that to remember where you came from. You don't have any register to register arithmetic. You've got to do everything to D. You don't have anything wider than 8 bits. So if you want to do 16 or 32-bit arithmetic, you've got to do it, byte at a time. There's no I/O. Console I/O, the minimum Forth system requires a standard input and a standard output device. And so you'd have to add a chip to create a UART, or you can do banging. And that's what this board does. This board, as originally shipped, does a bit banging. There are those 4 input bits. One of them is selected for the serial input, and the bit is used for the serial output, and you can do bit banging. I think it runs it up to 1200 baud, maybe, maximum, because you're doing it in software. So how do you, sorry?
The qubit?
The qubit?
Yeah, good. Qubit.
Oh, that kind of qubit. No, this is the, yeah, okay. So to port forth, you want minimum code space because you have limited memory. You want maximum performance because you have limited clock speed. The things that it's spending most of the time doing is things like next, and the entry point to a colon definition, and words for doing constants and variables and other things. So these are the main things you want to optimize for. Leaving a colon definition, and a little bit of optimization regarding shuffling data to and from the parent stack. So since this really has no endianness, this processor at all, there are no 16-bit data types. Everything is 8-bit. So you can make your own choice about what endianness you want as you're writing the program. You really don't have any intrinsic endianness in the architecture. So you could lay out the parameter stack and the data stack either way, big endian or little endian. You can lay out the, you can have the stacks going up or down. It's up to you what you want to do. And of course, the question about whether you can do indirect, direct, or subroutine threaded Forth compilation. So how does the set program counter work? Essentially, if the P contains 1, the current program counter is R1. R1 has the value 1, 2, 3, 4. And that means I'm executing location 1, 2, 3, 4 in memory, and let's say that location contains a set program counter instruction that sets the program counter at R2. So whatever R2 contains, 5, 6, 7, 8, that jumps to that location. So now I'm executing at location 5, 6, 7, 8. But the thing is that R1 is set to the byte after the SEP. So the SEP is like a kind of a function call or a procedure call, but it can only go to one of the 16 the 16 index registers. So it's like I have an instruction set with up to 16 call instructions, but no more. So I can't use direct threaded code because I only have 16 different destinations. I can't address all of the Forth words. So it's a 1-byte instruction, which is good. It takes very little space, but I can't address the whole of memory. So in terms of the stack design, there is an instruction that does a load and advance. That's the obvious thing to use for a stack pop. So that dictates basically that all the stacks grow from low to high, high to low. When I'm doing a load and advance, the register fetches the value from memory into the D register, and the register is incremented, so the stacks grow. As I push things onto the stack, the stack pointer decrements, and as I pop things from the stack pointer increments. There is a store and decrement instruction. It's kind of useful, but not great. It would be better if it was a decrement and a store, because that would be the opposite of the load and increment, but it's the wrong way around. And secondly, it only works on the current index register. So I can use that stxd instructions on one of my stacks, but not on the other one. And I chose to use it on the parameter stack and not on the return stack because that's where I do most of my arithmetic is on the parameter stack. So there are 3 options for threading. Subroutine threading can't be used because I don't have a subroutine call instruction. I chose to do direct threading because it's faster. So a direct threaded word starts with a call, and it turns out I only need a limited number of calls. I need one to do colon, I need one to do const, I need one to do variable, and then we'll talk about create. Create is a special case, which is a problem that I wanted to point out. If I want indirect threading, there is a FIG Forth implementation for the 1802, which is by definition indirect threaded. It is a lot slower. The next is at least 4 instructions longer than the next with direct threading, and the words are also larger. They're at least 1 or 2 bytes longer if you use indirect threading. So it's already been written. That's no fun. I wanted to write my own. So here's a direct threaded example how I do a const. So what I have a program counter. One of the registers is dedicated just for handling consts, and if I compile a const, I put the Forth header, I put a sep to this particular code that handles consts, and then I put the value that needs to be pushed onto the parameter stack. And the program counter, this program counter starts out pointing to this piece of code here, which basically loads the inline constant high byte first, pushes it onto the parameter stack, and then the thing is about these SEP instructions is I've incremented the program counter to here. Next time I want to call a const, I have to make sure that the program counter points back to the start of this routine again. So I always branch back to the location before the beginning of that routine. So there are a number of little routines like this in the inner interpreter, which all loop back to the beginning so they can be reused again. And that's essentially how I do the inner interpreter words. So there's one like this for const, there's one like this for variables, and there's one like this for colons. And I'll show you in a second how the one for how next works as well. So that's, I can compile, so I can const, it takes 3 bytes to compile a constant, excuse me. Oh, let's talk about the endianness first. So you noticed here when I push the, when I assembled this word, the high byte comes out first. That's really the only endianness. It's really an assembler convention more than anything else. The architecture itself doesn't have any endianness. So the high byte is first, so that means, to make it simple, I want to push the high byte on the stack first, and then I want to push the low byte second. So the parameter stack is stored most significant byte below the least significant byte. Now there's a problem. When I want to store doubles on the stack, the Forth ANSI standard requires me to put the most significant part of the double above the least significant part. That is something that's required in the standard so that you can do an unsigned single to double just by pushing a 0. That's the reason for that. But it means that I have to store my stack doubles on the stack, I have to store them mixed Endian. So the most significant byte to the least significant cell. This is not a traditional ordering. It's called a mixed Endian order. But it's okay. It's standard compliant. I'm not required to pick one or the other, and that's the way the doubles are stored on the stack. So that's the parameter stack. The return stack, I decided to do it the opposite way around, just so that I can do from R and R from and to R optimally. So I just do like this to move stuff from one stack to the other. So here are the registers that I'm used. Did I not show you the next? Maybe it's in the next slide. Yeah, the next one. So I've got a register for all the code words. I've got a register for next, so I can just do a next with a set program counter instruction. I've got one for colons, one for constants and values, one for variables, and create one. I'll explain what create one is. It's not a standard word. Another one for creates. And there's a thing in the compiler called a user variable. I had one for that, and I have one for execute. So those are the kind of the dedicated program counter registers. And then I have the virtual machine, the interpreter pointer, the parameter stack pointer, and the return stack pointer. And most of the arithmetic is done on the parameter stack, so I set the index register to 2, so that the parameter stack pointer is the destination of all the arithmetic. There's a few exceptions to that. The inner interpreter is 6 instructions. Basically load the thing pointed to by the Forth interpreter pointer into the program counter register and jump to it. So that's the, okay. I've got to do a demo then. Let me jump to the demo. Oh, this is an important thing I wanted to point out. Create versus variable. In ANSI Forth, they decided to merge builds and create, and that caused me a problem. Because at the time I compile a create, I don't know whether there's going to be a does or not. In FIG Forth, I knew if I saw a build that there was going to be a does, and if I saw a create, there was not going to be a does, and I could compile it differently in ANSI Forth. But in FIG Forth, they merged the two into create, which means that create is a lot slower than it needs to be in the case that there's no does. So if anybody wants to discuss that, it's just I think it's probably one of the few mistakes that the ANSI Forth committee did. Let me go to the demo. So this is the this is a simulator I'm running here. This is not the real hardware. And what I've done is I've created an instruction level simulator. This board is not powerful enough to run Forth, so I'm running an instruction level simulator, and I have a cross compiler, and I've a cross assembler, excuse me, and I've created machine code bootable image, and there's my Forth dictionary. This Forth dictionary implements all the core extension tools and string words that are part of the ANSI 94 standard. And I run the this is the test suite from Jerry Jackson and John Hayes, and it passes all of those tests. And I wanted to point out to you, the simulator keeps track of the amount of elapsed time. It knows how long an instruction takes. Those tests in real time on a real 1802 at 3.2 megahertz would have taken 2,500 seconds, or about 40 minutes. So there's an advantage over simulation as opposed to running it on the real hardware. Okay. So one of the challenges of bringing up this board is actually how am I going to bootstrap it. Let me bring it up. The whole thing right now runs, the dictionary and all the stuff runs at about 6.5K bytes. Can you see that? Yeah, 6,500 bytes. That doesn't fit in that ROM. I've got a way of bootstrapping it. I can take a subset of this and burn it into the ROM. That's about 3K. And then I can compile the rest in Forth afterwards. But again, that means booting time is going to be horrific because compilation, it takes about 1 million cycles to find a word in the dictionary. It's a single linked list dictionary, so compilation speed is a line or two, maybe a second, something like that. It's pretty bad. No, more than that. It's several seconds per line. Anybody any questions? I have other material. I ran out of time. That's all.
Right. Okay. Which starts now.
Okay.
Actually, it started 3 minutes ago.
Yeah.
Impressive to see how small how few the opcode bytes are in the assembly listing.
Device was done on 1802 back in the late 70s. Yeah.
Okay.
Yeah.
You write it
and
in
we
assembler?
modeled it in.
You write it in assembler?
Well, yeah. We
Okay.
wrote our own assembler.
Really?
Yeah.
I started with a cross assembler that I wrote that was actually based on a macro assembler for another processor.
Yeah. I can't remember what we in order to do it, but it was we had to split the divide up because there are other things we had to service. We couldn't do a divide. But I was curious, if Intersil still makes this, have they stepped it at all? Is it faster in any way? There's hardly any logic in it. I mean, you can do that in an FPGA and make it.
Oh no, there's a guy here, James Bowman, who after I did the presentation last month, he went away and wrote it in FPGA. Like
Yeah, exactly. There's hardly anything there.
There was a follow-on chip called the 1804
Yeah.
that had some more instructions, but the architecture died at that point, and nobody ever developed it further.
So they never made anythings that would actually do math in the registers themselves? There's no way.
There's only, you see, the logic is, the ALU is hardwired to that D register. It's an 8-bit.
I see. Yeah. Huh.
It makes the logic simple. You have fewer multiplexers. If the input to the ALU is always the D register.
Well,
This
it seems
thing
like
was-
arrays is a very pop thing. We've got this green array. We have an array of registers in the 1802. We've got that other array of processors in the propeller.
Okay.
And, oh yeah, that's another one, huh?
I did do a G4 port to a processor that had 72 cores, the company I work for.
Yeah.
But, Forth doesn't have multi-thread awareness within the standard, at least. I don't know. People do it differently. So.
The thing that I would think, what's his name? The one before, some of the stuff he had on the screen, it looked like things were starting to be arrows, but that wasn't code. That was just a picture. Now, what would happen if one used a two-dimensional array for text for compiling?
That's blocks.
Yeah.
That was the old block stuff.
But maybe it compiles as a graphic thing. So I could actually graphically draw a code around another code and determine how that works.
It's like a GUI for development.
Yeah. GUI and the see that's it. It's all based on. I mean, even when they say a register machine, it has a linear. It's like Turing with a tape going back and forth. But they don't have one that's a sheet, do they? They don't have a computer that's essentially a sheet that you move. You essentially move the logic by the point of interest.
The thing about esoteric architectures is that they're very rarely commercially successful.
Yeah.
Because you're telling people you're going to have to throw away your code and rewrite it. That doesn't work anymore. You have to leverage other people's code. You can't rewrite everything from scratch. Those days are over.
Yeah.
So every esoteric architecture.
A lecture once Bill Gates.
Yeah.
And there was a Sacramento Computer Club.
Right.
He actually came and gave a presentation.
Oh, that's cool. Yeah.
And he says, let's talk about software efficiency. And he says, there's only one thing you can do to make your software more efficient. He says, reuse of code.
Right.
He says, that's the whole trick. He says, it's reuse of code, and he says, forget about anything else. He says, because it's the only way you can really leverage stuff up to extremely high levels.
That's assuming that the thing you're reusing was efficient to begin with.
Well, I don't think he was.
Efficiency is less important. The programmer's efficiency.
Right.
In those days, when you had 5 microseconds per instruction, machine efficiency was important for a lot of these embedded applications. But nowadays, unless you're doing high performance computing or network packet processing, gigabit network packet processing, it's the programmer's time. And why do people use Python? As far as I'm concerned, Python replace Forth. There's nothing that Forth has that Python doesn't already have better.
Oh, is that right? Okay.
Right? I mean, the main thing about Forth was, rapid prototyping.
Yeah.
It's in Python.
Yeah.
And it's object-oriented, and it's, it's going to be...
Can you understand what's going on in Python?
Oh, yeah, it's a lot easier than Forth. I look at Forth program I wrote a week ago. I can't figure out what it does.
Yeah, I started to learn Python. I was doing scripting, stuff, and I used that.
All right. Okay.
I mean, Forth string handling is miserable in Forth.
It took me probably at most a place where I was writing
with new type of code.
Yeah. So much simpler.
Nowadays it's not as much of an issue. I mean, people say, the thing is those access to those darn libraries. It's just sort of like the whole thing with using, using Git. Then you say that they've already figured out how to do it, and all you really have to do is kind of talk to them at a high level, and it's done for you.
Yeah, but then Chuck is saying, forget about the libraries, you got to just rethink the problem, and you come up with something better.
Very, very welcome.
So you did this just because it was there and because you liked it?
Well, in 1979, this is my first.
Oh my God, this is an artifact. Okay, right. Oh my God, yeah, that's right.
The Apple II came out in 10 years. I couldn't afford it.
Exactly. Okay.
Sorry. Yeah. Shane, your talk. I'm really grateful to you for presenting.
No problem.
Anyway, can I get some of your...
You can download this book. Okay, slides.
You want to move away?
Let's get off.
You can get
Awesome.
my phone.
Thank you.
1 minute warning.
See, it looks like 14.
There's reality, and then there's numbers on the screen. Which do you believe in, George?
I just begun with. We keep the
It's a phone call for you. They want you to sit down and shut up.
You're coming into somebody else's file now, John. Sit down and be quiet. These all nuts.
In case I didn't say it before, thank you all for coming.
Oh, you're welcome.
Yeah,
Okay. Hello. My name's James. I'm a Forther, and the display here is run by the actual Forth machine. So I'm running the slides on the hardware that I'm going to be demonstrating. So you'll have to bear with me while I kick off my slideshow. So I'm sorry about the quality of the slides. That's because it's running on homebrew hardware, and I don't have an enormous amount of resources here. It's the 8-bit display adapter that I made a few years ago. And just before I get started, here's my fantastic diagram of how the slides are working. I've got a laptop up here, but all the laptop is doing is running as a serial connection into my Forth machine. Storage down here, and my display adapter here, the graphics adapter, the VGA. So
everything you're seeing here is being driven by Forth all the way down to the hardware involved. So if it goes wrong, that's why. Okay, so my motivation here, my big project is that when we want to do, can anybody tell what that is? Okay. I guess you have to be a long way away, because I have no idea. So we wanted to fly, we wanted flight, and what we actually got in the 20th century is, well, it's certainly air travel, but it's not exactly flight. It takes you from A to B. Well, I'm not complaining, we get all the advantages of it, but we have almost no control over the actual aspects of flight. And using a computer is a lot like that these days. We've kind of become so detached from the actual computing process that we have no real control over any aspect of the computer. Huge numbers of people fix their computers by doing the only thing that they have absolute control over them, which is switching them off then on again. That's really the last thing left to us in many cases, is to switch it off, switch it back on again. In fact, for some things, if you're an iPhone owner, you can't really do that. So what I'd really like is a computer that we have complete control over all the way down to the metal. People seem to want this when you look at projects like the Raspberry Pi project. That sells on the idea that you're in complete control over the machine. But of course, unless you're really, really into the Raspberry Pi, you don't have complete control over the machine. You can't install the cross tool chain and rebuild it if you're a regular person. It takes a lot of resources. So that's where we're at. I wanted a machine with direct control over every aspect of its operation. So as it happens, I'm on an early release program for a new CPU architecture. 32-bit embedded CPU, runs at 100 megahertz. And that architecture is what I chose to run a bare metal Forth on. It's called the FT900. It's from FTDI, the USB people. It's a single chip CPU, so 32-bit, runs at 100 megahertz, and it's one instruction per cycle. So a 32-bit embedded CPU, but it is an all-new instruction set architecture. It's not an ARM or anything else. It also has, I mean, that's the CPU core, but it also has a bunch of peripherals on the outside. So it's really meant for embedded system-on-chip applications. Has 256K of program memory. It's a Harvard architecture, so it's split between program memory, where the program lives, and 64K of RAM. And what's particularly interesting for a Forth implementation is that this program memory is just plain RAM. It doesn't execute from flash. What it does at boot is it takes its flash, which is also 256K, copies that into program memory, and then program memory is writable. So you can, just using a port address, you can write to program memory just as quick as, obviously for a lot of embedded systems, this doesn't matter at all. All they ever do is boot from flash and then run from program memory. But for a Forth that's compiling on the fly, this is obviously much better than having to compile into flash, which takes a really long time. Okay. The other thing is that this isn't ever going to be really running anything like Linux because of its restricted RAM size. So it's really aimed at embedded. Okay, so that's the target machine, and I've decided to build a Forth. What kind of Forth model am I going to use? Well, there's of course the old SVFIG Forth model where you have an assembly file. I think Harold showed us something like that, where you make a big and that's kind of appealing. Obviously, you have to start off in assembler, whatever. But if you end of my when I'm building several words in Forth, I'm thinking in pure Forth code words, large volumes of Forth in assembly language using assembly mnemonics. The other alternative, meta compilation, I've tried before, or cross compilation, I guess we'd call it these days. Repeating yourself. You have to define every word for the meta compiler, and then version of that word. So words if. You have to have two versions of if. You have the meta compiling if and then the native if. Something else this time modeled on Jones Forth. Jones Forth works a very simple way. It first creates a minimal forth in an assembly file, which gets you far enough to execute commands from the keyboard. And then effectively the rest of the forth is typed in to that minimal forth to extend it. So you get to the basic point where you can run just enough code to run an interactive forth, and then the rest of it is if it's being typed in. And so that's what I've settled on. So that's the kernel, the .s file, and then that gets us to the point where there's a command prompt. It runs almost nothing except maybe colon, semicolon, and a few basic words. And then the rest of it is all defined in high-level forth. So that's the progress. All right, next choice, just like Harold, had to use a threading model. And for me, I really wanted to make a forth that was actually useful and compete with C in terms of performance. And so that really you in the direction of threading these days. You can't really get close to C's performance unless you use subroutine threading and you're generating native code. So that leads us to actual code. Okay, so here's my code for us. These are addresses down the edge, just cut off by the projector, and there's this is a forth which we have lots of registers, so we can keep the top of stack in a register. Here's what an R0 is the top of stack. So here's what we do for 1 plus. We add 1 to R0, put the result in R0, and then return. And everything in this forth, because it's a subroutine threaded forth, is a subroutine. This is a 100 megahertz machine, so that's 10 nanoseconds, so it's 20 nanoseconds. And another 10 for the call, so 30 total. Okay, duplicate. No dedicated stack pointer. So DSP is actually just one of the registers. I'm just aliasing it here. So in order to do a duplicate, I move the stack pointer down 4 bytes. It's a 32-bit forth. I store the top of stack in the old data stack pointer, and there we go, duplicate. Okay. I want to take the top of stack, the data stack pointer, put it into R1. There's the actual add. There's the actual add in the third instruction, but here I've moved the data stack pointer up 1. This is how addition works. So if you keep the top of stack in a register, it saves on a lot of memory accesses, and that's the sweet spot. You don't actually save anything by caching 2 things in registers. So in register is where it's at. Okay, so we're in a subroutine threaded forth. So those are primitive words which were coded in assembly. So that was a section of code, and it is after compilation. So a high-level forth word gets turned into a long list of calls. So all of those words are just subroutines. This shows the label and then the subroutine entry point. And this is what the compiler actually produces. It's a lot like an indirect threaded forth. These are, in fact, these call instructions here are just like execution tokens. And every function, this is a bit like exit. That's just return. So it's fairly similar to a thread forth. After a while, you just forget about the fact that it's native code. All right, so a lot of thought has to go into the dictionary in Forth, because when you're compiling and doing a lot of things, then dictionary search time is a burden. Managing, particularly with the word list Forth extensions, is quite complicated. So what I really wanted from the dictionary search, a simple I didn't really want to implement hashing or multiple linked lists. I wanted Forth super elegant linked lists for its dictionary, but have a very fast lookup algorithm. Obviously, I have to decide on a header format. So here's the header of a Forth word. Here's my link field. And then here's the name, which is up to 32 characters long. This is a word. This is 32 bits wide. So 32 characters is up to 8 32-bit words. And everything's aligned on this architecture. It doesn't cope with misaligned data. So everything's 32-bit aligned. So when I'm searching for a name, I've got to 8-bit words I want to do a comparison on. So I can actually, I've got lots of registers. So during the search, I can load the word up into registers here 10 through 17. So my dictionary search becomes just loading words out of memory and then doing a 4-byte compare against each of these registers. So no more byte by byte string compares. I'm just doing word compares on the entire word. In fact, a word usually isn't 32 characters long. Here's a typical word which is 8 characters long, in which case I just have 2 registers, and I can super quickly tell, obviously most words are going to be rejected. As you're searching through the dictionary, most words are misses until you finally hit the word that's the match. So all of this dictionary search time comes down to about 40 nanoseconds, just 4 instructions to actually reject a word. You start at the end of the word. Does it match R11? No. Next try. So this whole thing becomes incredibly, particularly when you compare it to the way the dictionary search used to work on old byte-by-byte machines. It's amazingly quick. So we can search through the whole dictionary. I think we can do 2.5 million dictionary searches a second. So it's pretty speedy. Okay, so next important thing for performance is loop performance. When I did the J1 CPU, I struggled a lot with loops because they're actually quite tricky to organize in Forth. We've all, I think many of us have made Forth, and we've all struggled with how do you make loops efficient. But on a register machine, it's actually not very difficult, because what you do, it's not very difficult to implement the proper Forth do loop system, which on the J1, for example, was sort of a disaster in terms of performance, because it would try to keep the value of I on the stack and the termination value also on the stack. There's a lot of stack juggling on every loop iteration. But if you've got a register machine with a lot of registers, you just do the, you take the loop bounds and you reverse it, so you're counting from negative to positive, and then your termination point here. So we've been asked to count from 1 through 6, but instead we count from -6 to -1, and then we end when we reach 0. And in R29, my other loop register, I just keep a bias, and so every time I want to compute I add R28 and R29. And this is kind of a classic Forth technique, but there's not a lot of documentation on how to make a Forth these days. I actually had to look through Forth dimensions from the late 90s, where, oh yeah, everybody knows this, but it doesn't get talked about a lot these days. Anyway, the upshot is that if you use this technique, if you've got 2 spare registers, it's fantastic, because all you have to do is push these registers at the beginning of the loop, and you get the loop comes almost for free. All you have to do on the end of a loop is increment R28 and make sure it's not 0 and then loop. So that means that it takes 20 nanoseconds to do the loop. A loop body is just 20 nanoseconds. It's 1 increment, 1 jump. So this code here, 50 million, is a 1-second delay, because we do 50 million loop cycles a second. Okay, performance. So have my Forth running, it's doing okay, it's generating the sort of threaded code I was showing you earlier, and super important to get peak performance to put an optimizer in there. In the old days, we used to write optimizers just to make code faster, because that's all that mattered in the desktop world, was just speed. But these days, of course, we tend to think more in terms of efficiency. So the optimizer, which takes code and turns it into more efficient code, is more of a help in the area of energy, right? We're taking our algorithm and turning it into a lower energy algorithm because that's what's important for embedded. How does it work? We take the regular SVFIG compile word, which normally just writes into program memory, and then it hooks it, and then it puts it through this giant black box, the optimizer, peepholes it, and then writes it out into program memory. And this is one thing I didn't want to have is a system with any kind of memory allocation in it. When you look at super reliable systems like space probes, one thing that very rarely happens is malloc. There's hardly ever any mallocs in space. So this is a fixed size thing. It doesn't use syntax trees or anything. It uses a fixed size buffer, and if it runs out of buffer, it gracefully spills. So this is not your sort of classic tree-based optimizer. It's based on recognizing short sequences in the compiled code and then applying a transform to them. And here is an example in action. This is 3 CRs in a row. This is how it is compiled without the optimizer, just 3 regular calls. After the optimizer, this is the tail call optimization. It just spots when there's a call and a return and turns this one into a jump. This saves a lot of room because, of course, in highly factored code, your function length is quite short. So this saves 1 word in almost every function, every 4th word. One other thing I did was I did not explore optimizations which made the code longer. So there's a bunch of forths which run really fast, commercial forths, which inline the code like crazy. And that's a good idea on a desktop PC, but it's not so good on embedded. We'll just use up all of our available storage. So what I'm doing here is emphasizing transformations which either are space neutral or are saving space. Obviously, this is the very first one I did because it saves a word. Okay, this is another optimization. If you look at the code for something like 2 times, it's a 1 instruction long subroutine. This happens a lot. A lot of the unary operators are exactly 1 instruction long. So why call them at all? Because instead of calling 2 times, you can just inline the actual code that's there, and the net is the same. So this code, which was 2 times and then a call to 1 plus, becomes the inlined contents of 2 times, just inlined right there, and then a jump to 1 plus. That's the same optimization as I showed. Okay, now this is the last optimization I did, and this is quite a big one for performance. So here I've got, this is a 65, which is my limit, and I want to make a small word which does a comparison. So I think we saw earlier compiling conditionals is quite tricky. So what I've got is a pattern which recognizes, so here it is, it calls limit, which pushes 65 on the stack, calls greater than to do the comparison, and then this is an internal word. These together, this call to do 0 comp, and then the jump, or what actually implements a 0 branch, and this is the if statement here. So this is jumping around this call to ticket here. This can be rewritten because, like a lot of CPUs, we have a lot of words. What CPU designers seem to do is they put embed immediates into the words. Obviously, in a true Forth machine, then all words are the same and everything gets its arguments from the stack. In CPUs, real-world CPUs with registers and instruction formats, there tend to be a huge amount of effort and thought into embedding immediates into instruction words. And so spotting those cases where an immediate can be embedded into an instruction word saves you a bunch because everything happens in 1 clock. So here we take the top of stack and we compare it against 65. So the optimizer looked inside limit, saw that it was 65, saw that we were doing a greater than and a jump, and then turned that into an inline comparison of R0 against 65. Drops the top of the stack. We're still because we don't want to make the code any bigger. And then this is the conditional jump. So this whole thing goes from about 15 clocks to, I think it's 6. So everything gets 2 or 3 faster with this optimization. And this is a little bit of lumen. Okay, well, this is how the system boots. This is the beginning of memory. We've got the nucleus, that handwritten assembly file. And then fairly early on, as soon as I possibly can, I build the optimizer, because obviously everything that comes after the optimizer gets optimized. And if I started putting code here before the optimizer, it would not get optimized. So I want to minimize the amount of code that the optimizer doesn't see. And who shaves the barber problem, because the optimizer gets run a lot. It gets run every time any code is compiled. And so it would be really nice if the optimizer were optimized. Well, it's easy enough. In Forth, you just build it twice. So I've got my optimizer code. I build it once to build the optimizer the first time. And then I just compile it again and make a slightly better, slightly faster and smaller optimizer. It replaces the hooks that the optimizer first used, and hey presto, I've got an optimized optimizer. This works fine, but I've left a big hole in memory here. What a waste. All of those memory saving strategies are rather pointless if I leave a 3K hole in memory where the old optimizer was. Well, never mind. So now I build the nucleus, and I leave a marker down here at the end of the nucleus, the point where I want to actually continue. I shift the code generation pointer up to the top of memory, because this stuff's tiny. This is like 3K, and I've got 256. Got lots of memory, and I build the optimizer in high memory, the first cut optimizer. Then I restore and go back to this marker. The optimizer is still running in high memory. Nothing can touch it. And then I compile the actual proper optimized optimizer down here. And then I'm happy. This guy is long gone by the time we get to compile it. So everything's safe. So enough. Okay, that's it for compiling. I had my system have a core Forth. Seems to generate code okay. The performance is pretty acceptable. So then I'm starting to think about actually using the Forth and building the peripheral drivers to make it into a useful system for embedded programming in 6 minutes. Okay. Oh, wait. I have one more thing to point out. Okay, so I'm using this as a benchmark. This is the sort of classic sieve of Eratosthenes benchmark that we use to performance, but you can also use it as an energy benchmark. How much energy does it take to perform this operation? All right, so here's my graph. So here's an Intel Core 2. This is I've drawn microjoules here, how much energy it takes to execute the whole thing, and this is time. This is duration. So Intel Core 2, if you really want it to run fast, have a very low duration, but boy does it use a lot of energy. So it's a 17-watt CPU, and even though it only takes a few microseconds to execute it, at 17 watts, your energy total is quite high. This is logarithmic. So here's the quite a champion low power CPU, which takes its time. It's only an 8 megahertz CPU, but running Forth on it, it executes in a sort of minimum amount of energy. It's super efficient. FT900, this Forth, is somewhere in the middle of that range. This is it's not quite as efficient as the Intel, but it's a lot faster than the MSP 430. So that's where we fit in energy. Okay, now onto the peripherals, which is an idea of batteries included, which is, I am actually literally running on batteries here, but what I really mean by batteries included is you plug it in and it comes with a bunch of useful things. So I don't give people a Forth machine and say, now it would be relatively simple to drive an interface. No, I actually provide the driver. Okay, well, what's the most important thing for embedded, in my humble opinion, is GPIOs. if you've got GPIOs, you are an embedded system. If you don't have GPIOs, you're a desktop or a phone or something. So GPIOs are kind of the most important feature of any embedded system, just a simple in-out. One thing that I'm always finding is that GPIO performance on a lot of systems is quite disappointing. Here is a benchmark in Arduino code. We set a pin, we set it to output, and then in a while loop we go bring out ones and zeros on it. How fast does this C code run? Here's the equivalent in Forth. I'm going to take pin 13, set it to output, and then here I am doing the same thing. All right, here's some systems which claim to be embedded systems. Intel Edison takes 4 milliseconds to toggle the pin. So you can run at 223 hertz. That's what they think is suitable for embedded systems. Yeah, I'm thinking the CPU isn't the bottleneck. But I don't know. I see why they called it Edison. But you would have thought that's quite fast. So Arduino is 96 kilohertz, which is sort of middle of the road. It does okay, but there are ways of getting around it and using special APIs to get it to run faster. On this particular Forth, it's just 5 instructions. It's 2 cycles to raise the pin, 2 cycles to drop the pin, and then 1 cycle to branch around, which is 50 nanoseconds, 20 megahertz. So there's factors of 100 in the speed of it. Okay, what can we do with a GPIO? A protocol Dallas called one wire, which is where you use a single pin. It's actually also the power pin for the device. And in timed pulses on it, you send ones and zeros down the line. So here's the FT900. Here's a one wire. This is the classic one, I think, that Franklin's going to show us is the temperature sensor. So this is how you send a 1, and this is how you send a 0. The time base here is 60 microseconds, so it's not very difficult to get these pulses going in time, provided you can generate a GPIO changing fast enough. It's easy unless you're Intel, in which case, forget it. Okay, so here one on this breadboard down here. It's running live, and it's 71 degrees in here. Where is it? Yep, we're alive. Okay. So this is RGB LED control. So there's a brand of LED called NeoPixel which runs on a base, and they're quite tricky to drive because you have to generate a series of ones and zeros. The color into the RGB LED. So quite quickly, 2 microseconds per bit, and 24-bit color value for RGB. And the slack is 150 nanoseconds, so you've got to be kind of careful with the timing on that. And I have okay, so here I have one running on a tiny board here. So favorite color is green, of course. There we go. So this is actually running, this is the standalone version of this running on a battery, and got a little bit of a user interface there. So that's doing the RGB loading in 1-bit protocol. Okay, so last part is I²C. I am running on a battery here, and the battery is hooked up to a charge controller. So I've got some more Forth words to talk to the I²C controller on the chip. And you can see that we're out of time, but we still have 50% battery, and the battery's giving us 3.7 volts. And this is talking to the charge controller, and then a few lines of Forth to format it for the screen. Okay, there's something else, is that once you've written code for this on the system, how do you actually make it persistent? Because you're writing code and it's going into program memory, which is just RAM. Your code will be lost on the next reboot. So there's a interface to the chip's own flash memory to take what's currently in program memory and RAM and then back into flash. So on reboot, you get exactly where you were when you left the system. And that's every word is frozen into freezes on the next reboot. So flash is, if you like, just another peripheral. I have a FAT32 file system interface. The chip has an onboard SD. All these slides here are living on SD card, and it's reading the SD card. Here, that's C:, and then I'm going to of it. So there's no operating system here. So all of the file manipulation instructions are kind of a mix of operating system, DOS type conventions, but really they're just Forth words. C:, is the drive object, and then dir is the word that. So there you go. There's my. Okay. Next thing is that's running the ANTS compliance suite. The whole thing lives in files, and it just got included. And as you can see, it takes about a second to run. Hurrying through this, and the last thing, this chip have a 100 base. So I've got the old J1 network drive running on this chip. So that's also network driver, and that's and then I think I'm way over time. So that's it. That's all I've got.
Feel free to ask questions at lunch.
So if you, this is the handheld version. So I'm sorry, it's just a bare board, but. You can actually, do you want to pass it around?
Oh, I can.
Yeah, yeah. Okay, good job.
And
My battery discharged too quickly.
Fuck. This isn't working, man.
We're already running late.
Yeah.
Would you like to yield the other 2 minutes of your time to Nash?
Yeah. Sorry about that.
No, nobody does. It's okay.
Yeah, we'll do it
I think
later.
the thing to do right now is to shuffle off.
Okay, got it. Sorry. I have a problem with this. Technical difficulties.
Mike?
Yeah, grab.
Thank you. All right. Am I in camera, Dennis? Ish. All right. There's been a slight adjustment. We were running kind of late to start with, and so what we're going to do is Dennis's talk has been pushed to after Nash's talk. So hopefully the pizza will arrive on time. So we'll be eating while Dennis is speaking, or the pizza will be late and we'll be indulging in rapt attention to Dennis's talk while we wait for the pizza to show up. So Nash is going to make his way to the front. John's talk is going to be maybe after lunch or maybe at some other time. Technical difficulties. So I'm going to hand over the mic and nominally till noon.
All right, I don't have any fancy displays or anything, and hopefully I can keep my talk short. I'm going to talk about just sort of a realization I came to regarding Forth and doing devices and hardware. As many of you know, my hobby into retirement is making small circuit boards, the host processors that implement little devices that I sell on eBay. And I like to document them and, just fiddle around. It's a retirement occupation. And it's a number of the devices that are just use microprocessors to perform a single function, generate a crystal clock for a ham radio receiver, things like that.
But a number of the devices that I make have a serial interface to hardware that does something. Two examples of that are a data acquisition system that I have, where you have serial commands, and it reads analogs and exercises digital outputs and that sort of thing. Another example is the latest example, which is a radio frequency link. There's a small board that you can get on eBay for, I don't know, $2 or $3, but you need to talk to it. So I put a microprocessor on a board and implemented a serial port, and you can talk over the serial port, issue commands, and implement an RF link. And you can run it in various modes. You can run it in broadcast mode, where you talk to everybody, and then they put all their responses in a buffer, and then you can address them individually and get the responses that they would have sent in real time. Or you can do it in a loopback mode, where they just put everything in a buffer and send it back to you so that you know the link's functional. And then there's a data mode, where you can send any byte sequences, including zeros, nulls, I guess. Then there's another mode, which is a terminal mode, where a person it simulates a person sitting at a terminal. It doesn't have to be a person. It can be a microprocessor, a system with a serial link that has a script running it. But you, and the terminal mode, you can do things like escapes, and you have carriage return line feed, but basically it's ASCII text. And that's what the commands are, of course. So you just type in commands and use that to configure the unit. And you can also use it to send text messages to the other end. So you have a master station and you have a remote, both of the same code. You just have options to configure them as a master station or a remote. And at the remote serial port talks to another serial device of some sort. It passes stuff through. In the terminal mode or the data mode, it just passes whatever the user on the master station sends on, and whatever response comes back on the serial port comes back to the master station. I really didn't want to get in too much as to the functionality of this device, although if you want to take a look at it, see me at the break. But the devices that I have that take a serial port, issue commands over a serial port, and do things are very much like I had the thought and said, well, what am I really doing here? Where's my market, and what am I trying to do? You're selling these devices, and say, well, how would a typical user use these things? And one of the ideas that we've been exploring is say, okay, you've got something like a Raspberry Pi or an Arduino, or all the popular stuff out there. But in particular, a PC or Raspberry Pi running a script, and it doesn't matter whether it's a Perl script or it's a shell script, or whether it's a Python script or a GForce script. You got a serial port, and you can send a bunch of stuff out there. You can bring it back. You can collect it. You can post-process it. Not a fast process, but a process that is generally pretty useful for just sort of a fairly slow data acquisition, for instance, things like that. And it occurred to me that functionally what's happening with these small modules is very much like going back to the typical Forth development model. And the example that I would use is the washing machine example from Forth Incorporated. I don't know, many of you are familiar with that. But basically, you implement well-tested words that perform a single function, and you cobble them together to make fairly complex applications. You develop a user application language, in other words. So you've got wash and rinse and fill and things like that that are maybe operating solenoids and starting motors and stuff underneath. But basically, you can put all these together in a script, if you will, or in another Forth word that calls these things, and make some fairly complex things. Well, that's exactly what I'm hoping to do with these small modules, is that instead of going out and getting a development system for an Arduino or something like that, and building some stuff custom, an application, say, well, the GPS chip, and I've got a radio frequency chip, and I've got this and that, and I cobble them all together with some code and produce my little device. You actually just have a script with multiple serial ports, which is easy to do now with the USB to serial adapters, and you can have as many as you want to. And each one of these things are talking, and you could to devices like this, and you can make a fairly complex application just, say, doing programming in Python with the script. Is that okay to say Python here? Anyway, or Forth. G-Forth works fine as a scripting language. I haven't done it mostly because on my website, just because I'm trying to get a wider audience. Well, anyway, that's about all I really have to say, is the fact that what I'm doing is Forth in hardware. I've got words that I type in to the serial port, and those are Forth words, and they do things. They have little functions that they do. And in order to build a larger Forth system, instead of putting these in other Forth words, you're just using a script to issue these commands in various sequences and various ways to implement functions that are implemented on individual little pieces of hardware. So each one of those is a Forth word, if you will. And vocabularies, there's you can think of configuration words as vocabularies. For instance, I have a master station, then you have a number of different remotes, or one remote, but general case, you have a whole number of these radio frequency remotes out there. So, but you have the same code, and you configure it. You say master, or you say remote. You issue those commands, and then you issue some of the same words, but they have a different context depending upon whether you're a master or whether you're a remote. And so you typically, if you had two raw systems that I deliver to you in the mail, you would take one of them, hook them to a serial port, and say master, and then I have a word to save it to flash. And then I would take the other unit, and I would say remote, save it to flash, and now they would actually boot up as master and remote. Address is another example. I can say address in a master context. It says that's my attentive address. That's the guy I'm going to talk to. In the remote context, I say, well, that's my address. Set my address. And there's some other parallels. I don't want to take it too far. And the last thing I want to say quickly is my development environment. I ran into not a problem, but in developing with multiple remotes and masters and data acquisition systems attached to each one of these remotes, and trying to develop it and get it all working together, I ended up with, well, what's my development environment like? And the best solution I came up with was I have a Raspberry Pi, and I just attached a USB hub to its port. It's sort of limited on ports. There's a new version out that's got more ports, but basically I hooked a hub to it, and on the end of each hub I just put a USB to serial adapter. And of course, Raspberry Pi is running Linux. I'm using the same Debian Linux on my host PC, and I do everything SSH into the Raspberry Pi, and I bring up terminals. So I got multiple terminals on my development system, and I can do things like sending commands to the master station. I've got another one up that says, well, at the far end, what response is really coming out the serial port, and how I can look at the response for the remote, and I can have multiple remotes and screens. And all I have to do at the master station is to the compiler runs on it. It's G-Forth, and well, actually, I'm programming these in my Forth, courtesy of Charlie Shattuck. But G-Forth is basically what hosts my Forth. And so I do all the compiling. I generate a binary load file for the microprocessor that I'm using, and then I just send that over SSH, or well, SCP, copy it over to the Raspberry Pi, and then the Raspberry Pi actually programs the chips through a programmer. And I can have any number of different little probes into all of my remotes using that model. And it has worked out real well. Nothing too earth-shaking in that realization, but and that's about it. Are there any questions? Okay. I'll have this available for people. Yep.
That's why. Now we can hear me. And I'll pass these around. This is I now work for Fitbit, and that little guy is a computer. Is one of their first ones? It's just a pedometer, or mostly a pedometer, with a web interface. And this is the little computer inside of it. This little dinky thing. It uses Bluetooth Low Energy. And people have swallowed them, but the glue doesn't hold up to hydrochloric acid. Is there a camera attached? No. There is no light source either. They had another one that they had to pull from the market because some people are sensitive to some rubber. And they had a sensitivity issue. So this is one that they just introduced now. This is the replacement for it. It's again a pedometer, but it's got a better screen. It's got an actual screen on it. This one is the almost identical, but it has a heart rate monitor. Interesting thing about the heart rate monitor is it works better on the back of your wrist than it does on the front. You have front on the front side, or if that's the front side, you have tendons. Tendons reflect light. It works better on the back. Interesting little discovery. And the fourth one is actually a watch. And again with heart rate. And that one, the heart rate is coming, the one previously of the heart rate is coming out soon. That will be on the shelves probably by the end of the month, maybe. The watch next year. So that is what I'm doing for jobs. I just got there a couple months ago. This is a list. It is not using Forth. yet. I have been watching the job market for quite a while now. If you watch my career and you looked on my LinkedIn, I've had a few jobs since 2005. After I got laid off from Apple, I went around the country, have come back now, and still getting interesting layoffs of jobs. So I've been looking for a while. This is a snapshot of last year of the ones that are Forth. Since getting laid off from Intelisys in Colorado, I have not been paid to write Forth anymore. I don't get paid for Forth. Even these jobs that merely mention Forth, it's not a primary thing. None of these are primary in Forth. Forth has not done that for a while. But there's some interesting names on here. Ford Motor Company was one of the interesting ones. Leidos, no. You don't get a lot of information on any of these. And this spreadsheet I have made available if you're on the SVFIG list. It will also be published eventually, that I'll get something back to Dave on something that works. Some of the links are very long. We got to work out how to get that to everybody. This is on Google Docs, and that is public. That I sent out this last week. The job descriptions don't say much, as job descriptions never do. But it at least is a job description. And some of the links don't work anymore. That one's back last year. That's back last year on the Ford. The ELO Touch was an interesting one too. I've got 2 of those on ELO Touch. I actually interviewed there. They didn't want to give me enough money, and I was working at Barnes & Noble, and so Barnes & Noble paid a lot because there was no equity. But ELO Touch is here. It's in Milpitas. They do touch controllers for a bunch of systems. Very nice company. Didn't want to pay me enough. They actually have a touch system that is written in Forth. Pretty much anything on the East Coast, the Virginias, the Marylands, those are mostly defense organizations, and defense organizations, typically those ones require a polygraph, security, and they're doing some Forth. Don't know what they're doing in Forth, but they're doing some Forth. Bechtel was interesting that they're doing malware analysis, and must use a little bit of Forth. What else is interesting in here? Amazon, you'll see a few places, mostly up in Washington, a little bit in Irvine. I'm getting to the point that I'm tired of moving. So I want to stay here. Yes? Is that an open firmware one? Okay. Okay. Interesting. This one here. That would be one of the few remaining open firmwares that are still alive. Open firmware in C. Oh, I didn't think anybody did that. Mitch was fighting that?
But there was a group trying to do open firmware in C in the very beginning of firmware, and they were competitors.
Oh, interesting. I hadn't heard of that one. But so just to review over the last year, there aren't many of them. There's only about 20 of jobs mentioning Forth, and that's all we've got left at the moment. Hopefully we'll do better, but we'll see how this goes. It has now become a very sweet spot for what we do, small embedded systems. That has become a sweet spot for the wearables. Wearables have become very big. I did want to show you a teardown of the Fitbit device. And pass that around too. Tiny, tiny boards. But these things have become very small. Very small. We are very useful again. Just as our talent and the language. Now, how I can get this language working in a development environment for Fitbit, I'm working on that. We'll see. They don't know. I haven't told them yet. I haven't showed them anything yet. I don't have it working yet. But we might become valuable again because we're small. And that's about it. Yes? Oh. Oh. I have there's a place called Indeed.com. Indeed.com searches all public job sites. And they have a crawler that goes and looks for all public job sites. And you can write your own search terms for these. And my search terms for Forth, because Forth is used inappropriately, as we would think, my search terms are a lot of places where Forth is used and I don't want to see. A lot of them come still through my filter, and those are the ones I'm interested in. I still get probably about once a day that I'll get something. Most of them are inappropriate still, that people are using Forth instead of F-O-U-R-T-H, where they intend F-O-R-T-H, or Fort Worth, or other misspellings. And there's a few of the bringing things forth, and back and forth. Yes, yeah, and there are a lot of those, mostly, well, you can see from this spreadsheet the frequency. 1 or 2 a month. It's about what I get of something that's actually relevant. And I post those up onto our mailing list. They're there. Yes? No. No. I have given up, other than the ELO Touch, I have given up looking for anything. I need to make a living. And, yes?
Noticing that, not picking this list, but things involving power recently over the last 35 years. It looks like very, very low power stuff.
Yeah.
And extremely large power stuff.
Large.
Are active and nothing.
Large power on power grid. I know a lot of this stuff. Yes, and from the power grid. Schneider. Yes. The I haven't seen a lot of that for Forth yet, but I think so too. I think we are hitting a sweet spot again, and we'll see what happens. Yes.
This might be a project that was put in several years ago, but space vehicle with a Harris chip just right on top.
Yes, I was going to mention that in passing. I noticed that one was Forth. Those are the Chuck's Novix chip. It is done in Europe. And actually, there's probably more activity in Forth outside of this country. It's happening, but under wraps. It's typically not talked about much. You didn't hear anything about the comet chaser until it was just about to land. And then the Forth people, it's been a fairly big topic. Yes, that's a Novix. It's the Novix. It's the Harris Novix. It's the RTX. Yep. Yep. I can't tell, as I was mentioning, we can't tell who watches this. Typically, people do not join the stream as it's being produced, and we don't want a lot of people there because it spreads the spectrum too much. The Hangouts then dump, when you go Hangouts on the air, they dump to YouTube. And quite a few people listen to the YouTubes, both now and later. But we have no way of knowing who's listening. Unless they send something on the email and say something about it, we have no clue. And that's sort of nice. I'd rather it be anonymous and let anybody view right now. And it's been very popular, especially when we mess up.
Well, we know at least one person from Switzerland is watching the feed.
Cool, cool, yeah. Any other questions? Huh? Yeah. The comet bounced, and they had some problems, but it's still successful. As I think most of the Forth experiments we've saved, it's been able to be saved. They had to reboot it? Well, yeah, probably lost power too. Yeah. They've been having all sorts of issues. But any other questions? Okay.
Kevin's outside waiting for the pizza, so we're officially on break.
Okay.
So just to let everybody know, we're officially on break. So what we're going to do, now is, well, I'll cancel my video feed just so that we can not bore you to death. And I guess when we come back, I'll kick the video feed back on. Or are we just going to leave? Do we want to?
It doesn't. It might just well. I don't see any reason why not.
Oh, I see we have some chat activity here too, although that's between Greg and... Greg is telling me to keep the stream going. Okay, so I will keep the stream going. Yeah. Yes, okay. So let's keep this stream going, and I will meander a bit, I guess. Okay, okay, excellent. So I'll do that then. So I'm going to turn audio off, the mic, but we will keep the video stream going, and I will be able to hear whether or not audio is happening.
Hello, Dennis. Hello, Dennis. Hello, Sam. Hello, Sam. Are you hearing me? Good. All right. Well, that's the only thing I wanted to make sure. You've got the video too? And so if you made me presenter, you'd see me full screen. And I can select me and see what that looks like too. Okay. All good. Thank you. Appreciate it.